Hello students, today's class will start off with brakes, the part 2 of your fourth module. So first part included is clutches. So clutches, I think they're done. So if any doubts are there in clutches, you just let me know the WhatsApp or you go through the videos already posted on YouTube. We'll start off with brakes. So brakes, another unit topic, which is a little bit larger than clutches chapter, right? So it has two divisions which has one derivation each. So in this module you will have four derivations, two in clutches and two in brakes, right? So brake, you can see, let me define it. So it is used as a mechanical device. It is used to absorb energy possessed by any moving system or mechanism by means of friction. So friction is the main working phenomena here. So both clutches and brakes work on the same phenomena, but it's quite opposite in usage. So clutches engaged to move the vehicle, and brakes engaged to stop the vehicle or even slow down the vehicle. So not only vehicle per se, it is used to stop a rotating drum or a disc or even a machine vehicle anywhere. So it's used in multiple places, not only automobiles. So most in automobiles, if you check, it is mostly used to slow it down or bring it to rest, right? So it's used to absorb this kinetic or potential energy, or sometimes both. Okay, so how both? If you ask, suppose you assume you have parked a vehicle downhill, so in that case you have to engage the brakes, right? So thereby you're arresting that potential energy in that case. The kinetic in when it is moving, right? Not only automobiles, it's used in also elevators, lifting systems, hoists, etc. So brakes are integral in our daily life. The physical classification of brakes, uh, depending on the medium used, you can see there are pneumatic, hydraulic, so laser. So there are pneumatic, hydraulic, electric, and mechanical. So for our course, we'll be concentrating only on the mechanical brakes. So whereas you can research other you know, kind of brakes, either pneumatic, hydraulic, or electric brakes. These are all presently used. So for this course point of view, we'll just concentrate on the mechanical brakes. Okay, so these are all equally used, very sophisticated machinery and other kinds of stuff. So mechanical brakes are further classified into a band brake. So band brake is the one which okay, let me oh, it's on behind. Okay, so check it out. This is the uh, shoe brake. Okay, the second one. Okay, band brake. I just put it on the other side. Okay. This is a band brake. This is called a band brake, where you have a flexible material. So it is actually some kind of a copper ring inside of which we have bonded material such as leather, okay, or any other friction material. So outside only the envelope will be a small thin piece of sheet metal upon which you would have mounted the leather or asbestos kind of thing. And once you engage the lever, what happens is you have that braking action. Okay. So the friction material or the leather, it starts absorbing all the rotation and thereby slowing down the vehicle or the drum, which you can see here. So we'll be designing this type of brake also. the band brake. So the one which I showed you was a band brake. Okay, and this is a shoe brake. This is called a shoe brake. This is a single shoe type. So this here is called a shoe, which is made up of friction material, either leather or asbestos. You have a lever which is pivoted at one point, and you have force being applied at one portion. So when force is applied over here, you can see there is absorption of the torque or power by this friction material, and thereby you have that stopping action being taking place. So also you can see there are dual shoe types. So the same shoe will be on the opposite side connected to the mechanism here. So when you apply the force, both engage simultaneously, and thereby you have a double action. Okay, so you have a shoe brake. Similarly, you have another band and block brake. So band and block, it is similar to the band brake, but what is the difference is you have an extra material coming out of here. So extra, brake material over here, thereby extra block you can see. The extra block, and it is connected to this band, and this is used to obtain lesser and more curve surface area. You see here, the amount of area covered, circumference covered for the drum is fixed. Okay, so but when you add another block over here, you can control another block over here, and this rope connected to that port, right? So these are the three basic types of brakes which we will be designing. Okay, the band brake, band and block brake, and the shoe brake. Okay, and here also you have subdivisions, external and internal. So the one which I showed you was external. This one is external. Similarly, you can put the same shoe inside, and you can put some spring mechanisms, and you can engage that using a lever of similar kind, and that is called an internal. Most trucks nowadays they use internal, but the mechanism is the same. That's why, since this is easier for understanding how this brake, the shoe brake works, we have just given you in syllabus that this is the one which will be designing. So these three basically band brake, block or shoe brake, and banded block. So these three will be designing in this module. And similarly, you have cone and disc brake. Cone and disc brake, I think we have done it on clutches, which is similar in operation. Similar, only engagement is a different conditions. That's the only difference. Okay, so before we go into the design procedure, we'll complete the derivation first. Not that clear. Let me switch. I hope this one is clear. Okay, so check this out. We have this point here, this pivoted, and this is where you are applying the force. This is one single link. So on this link, you have brakes. That is the shoe. The shoe which is made up of friction material being bonded rigidly, and this is your drum, either hollow or solid. We are worried about only the diameter here. So this is the drum which is required to be stopped. So when we come to force analysis, so take a center position of this drum and extend it further. So once the brake is engaged, these are the different positions the lever will encounter. So once you engage with the force, okay, so this is how the positions they differ with respect to the lever here. So assume any rotation. So we'll take two cases, either clockwise or anti-clockwise rotation. So first, in general, we just define how the forces are acting. So forces Fn here is a normal reaction, between the sheave and the block. Okay, sheave. This is another word here. Sheave means this drum diameter or sheave diameter. So this drum is also called as sheave. Okay, so that's what he means by sheave, and this is a block. Block is the grayed out portion here. Okay, so that's the block. So the normal reaction you have in the upward direction, and perpendicular to that you have mu times Fn, which is nothing but the reaction, not the reaction, it's tangential. The tangential force is mu times Fn, where mu is the coefficient of friction, and the pin reaction you have it over here. Fr will be acting here. This is a pin reaction because this is pivoted at this point. Okay. So C is nothing but the distance from the pivot point. So we'll be analyzing from this point, taking moments of this break here, and find out what is the equation of force, how much force is required so that you have the braking action. Okay, so we'll continue from this point. It's not that clear. This image. Okay. Okay, so from looking at this diagram here, and taking moments, there is summation of moments about this point here. This point, let me just name it something. So let me just name this here as O. Oh, let me name this as O. Okay, from this point here. So I'll take the summation of moments about this O, and this should be 0. So that means, looking at the diagram, so this is force times acceleration, not acceleration, sorry, this distance here. From this point, we are taking from this point, right? So this force is applied along this distance. So this is inducing an anti-clockwise motion. So let's take anti-clockwise as positive. So F into K, and next force. The next force is you have Fn here. The Fn acting on this lever, which is inducing a clockwise movement at a distance of b, right? So clockwise Fn times b. So this minus y, because it is inducing an anti-clockwise motion, Fn times b, and you see here the last one, you have mu times Fn. Okay, so this tangential force, mu times Fn, is the tangential force acting here. Okay, at a distance of c, at a distance of c. So this is also inducing counterclockwise movement. So therefore, counterclockwise we have taken is positive. So plus mu times Fn into c. So that's it. That's all the forces acting. So you have F at a distance of a, Fn at a distance of b, and mu times Fn at a distance of c. Right? So 3 forces, this is equal to 0. Okay, this also you don't need to memorize. This is also given in equation 13.16. Okay, so no need to even memorize this, but it's evident from the diagram here, right? So therefore, we can simplify this in the next step, like F force equal to Fn B minus Fn times mu times C whole divided by this whole divided by A. Okay, so here you can take that Fn as common, so therefore Fn taking common, so B minus mu times C over A. This is also here, not necessary, but just extra information. So this is the generalized equation what we got here now. Okay, so from here there are three different possible cases. Okay, so how three different possible cases you ask? See here, if here B is greater, okay, B if it is greater, that means this will be positive and this value will be positive, which means you need to apply a positive amount of force. Some force need to be applied, right? So this is a desirable condition. So if this B is nothing but distance from the pivot point. So if B is lesser, that means this is negative, right? So if it is negative, that means you don't need any force. That means it will be almost engulfing this sheave here. So thereby no force is required for braking, which means the brake itself is useless, right? So that's where you have the splitting here. Okay, so let's go here. So this is case one. So this derivation you see is common, very simple, very common, and from here three cases will subdivide, and any one case may be asked, or maybe two cases. That's it, depending on the number of marks is asked. Okay, so I can take here case one. Case one is where B is greater than mu times C. So what happens in this case is your B will be positive, right? So if B is positive, this whole thing is positive. So if this whole thing is positive, that means you would need some finite amount of force, okay, to be applied. So let me write that also. So F is positive and as F is positive, you can say force F equal to F um, times F n B minus mu F n C. So this portion here, so this portion here, okay, this thing here. Okay, so this part it decreases the amount of force required. Amount of force required to apply brake. Okay. We increase this portion here, which means lesser and lesser amount of force. So this makes sense. You see, mu is the coefficient of friction. To increase, what happens is that if you increase the coefficient of friction of the particular material, or you use that particular material, then the force required will be lesser and lesser. Similarly, this C value here. The C value is nothing but the distance here. You can see. To increase the distance, what happens is this brake plunges more and more into the sheave, and thereby you have the braking action, right? So Let's continue. So that is, it helps in braking, you can say. It helps in braking. So this portion here, you can either increase the value of mu or you can increase the value of c here. So both increase the, what do you say, probability of reducing the force that is needed. And this is a required condition. Okay, so this condition is called, you can say, this condition is known as self-energizing. Self-energizing brake, and it is very desirable. It is a desirable condition. So this condition is very desirable. Self-energizing. So this may be asked in 1 mark and 2 mark questions also. What is self-energizing? Okay, so self-energizing just means that you need some force to be applied so that you have the braking action. Okay, so that is called self-energizing condition, and this is a desirable condition. Okay, you can just write this equation and you can specify that B should be greater than mu times C, and the force applied will be positive, and thereby is a very uh, required condition. Desirable. Okay, so let's move on to case 2. So case 2 is when the B value of B equals to mu times C. So see what happens if B is equal to this. So that means this is 0, right? So that means force will be 0. This entire right hand side of this equation here, I just name this as say 1. So the entire right hand side of this equation will become 0. So if that becomes 0, which it means no external force is required to engage the brake, which means the vehicle will not at all move if it's in stationary, or when this happens in while you're driving, then you're gone. It's self-locking. Okay, so let's say in this case F equal to 0, which means no external force. External force is required for braking action, or let's say just braking. There is no force required for braking, and let's say this condition is known as self-locking brake, and is undesirable. This condition is not desirable. This self-locking condition is undesirable. Okay, so this again we for 2 marks, 3 marks it may be asked. What is the defined self-energizing, self-locking condition? The last case is case 3. Case 3 is when B is lesser than this value, mu times C. So check out this. In this case, what happens? Okay, so this will be negative. this entire right hand side of equation 1 will be negative, and that means you don't require any force, and in fact it is already grabbing hold the entire sheave here. So this is called uncontrolled braking. This condition is called as uncontrolled braking, and this is dangerous. This condition is very dangerous. So F will be negative. Okay, you can say this is a dangerous condition. Dangerous condition, okay, resulting in uncontrolled braking. And this is also called as grabbing. And grabbing. So this also might be asked for like 2 marks and stuff. Grabbing. Okay, it just grabs the entire sheave. The shoe just grabs the sheave, and thereby there's no possibility of even moving the vehicle. Okay, so these are the 3 conditions. So which should be taken care when you're designing stuff. So this condition, whatever I define, is depending on directions. So first case, let me assume here, I assume this as clockwise. Let's say assuming clockwise, direction. So I have derived this equation. Okay, for anti-clockwise, just the forces they reverse, which means this equation here will be for a clockwise condition. Okay, so for anti-clockwise, just the opposite. Right. So this is for clockwise condition. And for counterclockwise, the same force F is given by Fn times B plus mu times C over A. So this is given in equation 13.16D, and this will be in 13.16C. Okay, vaguely around this portion. Right. So this is C. Clockwise, counterclockwise. Whenever given in the question, you need to refer to that particular figure. And the same phenomena again follows for this also, as the directions are different. And one more thing, if a small note. So sometimes in the question it will be mentioned like for long shoe. Long shoe. Shoe means this thing here, the grayed out portion here. That's called the shoe. Suppose in the question it is mentioned as a long shoe. In that case, pressure along the length of the shoe is not uniform. Okay, so because there will be some amount of buckling in the shoe because of the extra length. So in order to, if the question is stating a long shoe, then what do? You take mu dash. Instead of mu, you take mu dash and make it equal to mu over mu into mu sine theta over minus 2 theta plus sine 2 theta. This is given in equation 13.16 m. Okay, where mu dash is the equivalent coefficient of that friction. So instead of mu here, you just use mu dash. You just replace this mu over into this mu dash here. And what is theta is? It is the half angle. Let's say 1/2 angle of contact surface. So this data will be usually given in the question. If the question mentions it's a long shoe, that means this theta will be given, and what is the deflection of that longer shoe. Okay, suppose we have the shoe like this, and let's say we have this drum, uh, the lever in this fashion. Okay, and you have that shoe. So you have very long shoe, let's say like this, very long shoe. So once it starts rotating in some fashion and it wants to use the braking action, that means you have a little bit of deflection like this. Okay. Okay. So this we'll take as theta. This will usually be given, okay, in that equation when we are using. So this is when only the long shoe is used. As a long shoe. Okay. Only when this is given you do that. Otherwise we'll use this original mu which is given. Right. That's what simple derivation which will be asked in your exam. Um, and also these concepts, self-energizing, self-locking, and grabbing. These conditions you should be aware of it, right? So let's go back to the presentation. We'll start off with the design procedure. So step one, material properties of the friction shoe. Suppose in question what happens is usually the material for the shoe will be given. Okay, and so in that case you should take the value of mu and p pressure from the table. So this is the table 13.111. So from this table just extract the values. Okay, whichever material is in contact and what is it contact with. So let's say leather on metal or wire on asbestos on all these things. So whichever material is given, depending on that whether dry, greasy or lubricated. So this data also will be given in the question. Also the allowable pressure, whichever is given, we need to take an average of this. Okay, or you can take any value in between. So better take an average of this and note down the material, the friction, coefficient of friction mu and pressure P. So once that is there, this here is small p, and we'll find the torque next, as usual, same as that of from gears, clutches, even continuing. You have the same equation. Right? So find out the torque acting on the drum. Step 3 will be the normal and tangential force, Fn and Ft. Fn is given in equation, whereas Ft is in the diagram. You need to check out the diagram and then note down the value. Right. And step 4, you have the braking force. You need to find out how much braking force. Again, direction wise, this is the formula differs. It's given in C and D, the consecutive equations. It's clockwise or anti-clockwise. You need to decide and find out that particular braking effort or force. So you'll check out the note. Sometimes braking effort will be given or the force will be given in the question. Then check for self-locking or self-energizing. So this condition we need to verify whether if it's self-locking, this is undesirable condition of self-locking is undesirable. Then self-energizing is the desirable condition. Whether your brake fall into this category, you need to check it. And step 6, the last step is finding out the dimensions. So once you find out that the brake can be used, so in that case, you find out the key dimensions. That is width of the brake lining or sheave diameter, and even that length of the links, all those things. Finding out the dimensions. And this is the table. So this table is for this thing here, width of the brake drum. So for if once you find out the diameter, so for that particular diameter, you have the width of the brake drum given. The width of the brake drum you need to extract from this thing here. Right. We'll stop at this point, I think. Any doubts so far? You can just let me know.